Hi, my name is Jonas and I welcome you to this video on Mobile Robot Tool Center Point Position Control. To control the Tool Center Point, or short the TCP, we first need to know its position and orientation. In the video about Mobile Robot Kinematics, we have seen the forward and inverse kinematics of the TCP. The link to the video is in the description. We will now briefly recapitulate what we have seen. With the forward kinematics and odometry, we can calculate the global translational and angular velocities and the global position and orientation of the TCP from the wheel velocities. For this, we use two Jacobian matrices, a rotation matrix, and two integrator blocks. With the first Jacobian matrix, we calculate the robot's translational and angular velocities in the robot frame. With the second Jacobian matrix, we calculate the translational and angular velocities of the TCP in the robot frame. Then, we transform the translational velocity of the TCP from the robot frame to the global frame with the rotation matrix. And finally, we integrate the translational and angular velocities to get the position and orientation. With the inverse kinematics, we do the exact opposite. Therefore, we calculate the wheel velocities from the global velocity and orientation of the robot using again a rotation matrix and two Jacobian matrices. With the rotation matrix, we first transform the translational velocity of the TCP from the global frame to the robot frame. Then we calculate the robot's velocity in x and its angular velocity with the first Jacobian matrix. The velocity in y is 0 by design. And finally, we calculate the wheel velocities with the second Jacobian matrix. After this short recapitulation of the forward and inverse kinematics, the main question remains: how can we control the position of the TCP? Obviously, a controller is needed for this task. The controller has the actual and desired global position of the TCP as inputs, and the output is the necessary global velocity of the TCP. From this velocity, we can then calculate the wheel velocities with the inverse kinematics. But let's have a closer look at the controller. In the controller, we calculate the global position error E and divide it by a time constant tau. Further, we also calculate the time derivative of the desired position. Then we sum up the two resulting velocities for the TCP and limit its value with a saturation block. With this control structure, we achieve an independent control in the x and y direction, and due to the saturation block, we can ensure that the velocity of the robot stays within certain boundaries. If we want to maximize the dynamics of the controller, we can express the inverse time constant 1 over tau as omega 0 divided by 2 times d. Omega 0, on the other hand, is the task frequency divided by 3.2. The derivation of these values was covered in the video about control parameters. The link is in the description. A downside of the independent control in the x and y direction is that the TCP does not move exactly along the error vector between the current and desired TCP position. If we want the TCP to move exactly along the error vector, we need to modify the control algorithm. We still calculate the global position error E. But then we take the Euclidean norm of the vector, multiply this value with omega 0 divided by 2 times d and limit it. To get back to a vector, we further calculate the unit vector of the error E and multiply it with the limited velocity. With this control algorithm, the TCP moves exactly along the error vector E. Thank you for following me through this video on TCP Position Control, and I will see you in the next one.